Hello students and welcome back to 1631. Today I'm going to be going over our second assignment that we're going to be doing this week. So last week we talked about Coulomb's law, so now we have a basic understanding of how charges works and the force between charges. So this week we're going to be moving on to looking at electric fields, or performing the lab called electric field around a conductor. So before I move on to what we're going to be doing this week, I want to revisit the ideas that we covered last week because they're kind of building off of each other. So last week, like I said, we talked about Coulomb's law. So we understood when we were looking at Coulomb's law is that when you have a charge right here, like a positive charge and a negative charge, that there's going to be some force between those two charges. So get in that mindset that we have these invisible forces and we're not really sure what's going on. Well, one of the next things that we can start to wonder about is okay, I understand that these two charges, they have this force on each other, right? We understood what Coulomb was doing and why he was wanting to do it, but now what's happening in the environment around these charges? So we're going to start thinking about these things called fields, right? So now let's say what happens if I'm standing right here, or we put a test charge right here? What is the forces on that test charge? So we're going to expand into that. And Faraday, he was fascinated by this, and we're going to start talking about things known as electric fields or magnetic fields. Now Faraday, he was the scientist that came along after Coulomb, and he started studying magnetic fields or electric fields. Now one of the things that I want to point out is I know in a lot of the diagrams I show you guys magnets because I feel like everybody has played with a magnet when they're a kid. So everybody has an idea how a magnetic field works, or they could at least associate it with something that's easier to see. Now there are differences between electric fields and magnetic fields. It's important to note. In our lab we're going to be looking at electric fields, but they're very similar. And as you advance into physics, you're going to learn that there are mathematical relationships between electric fields and magnetic fields. But for this introductory purposes, I just wanted to give examples so you guys could relate it to something in real life. But we're going to be looking at electric fields, and they behave very similarly to a magnetic field. Now, let's define what an electric field is, right? So Faraday, or some of the early physicists, what they wanted to do was they wanted to try to describe what is happening between two charged particles. Let's say this one's negative, this one's positive. What is the electric field at these points? So what the electric field describes is it's the electrostatic force that would be exerted on a test charge, or a positive test charge, Q naught, at a given point. So if you remember from last week, this is Coulomb's equation, right? Now this equation was simplified algebraically because now we have a test charge Q naught, and it was simplified. But this equation comes directly from Coulomb's equation, and if you work out the units to this equation, you're going to realize that your SI units are going to be known as volts, or it's going to be voltage divided by meters. That's how the units will work out and cancel out. So basically what we want to know is what is the electric field at given points. So we're going to use these diagrams to kind of show us what the electric field is doing, how it's acting, and it's going to give us some information. Now these diagrams, they look a little complicated, but once you learn how to read them, they're very, very simple to look at. So I'm going to give you some points on how we're going to read these diagrams. So the first point I want to point out is that when you're looking at these diagrams, the arrows are always going to point to a negative charge. So like if you look at this diagram here, we have a positive charge, a negative charge. All the arrows are pointing towards a negative charge. They will never point towards a positive charge. So here you have a positive charge here, a positive charge here, and you can see that the arrows are pointing away from a positive charge and they're deflecting. They do not like to point towards positive charges. So your field arrows are always going to point towards a negative charge and away from a positive charge. That's the first point. Now, there are going to be some things that you might not see them on every diagram, but in some diagrams you'll see them, and you're going to see these lines that are known as equal potential lines. So what does that mean? Along this line, that means that the voltage is the same, right? So let's say that on this circle, you measure 5 volts. On this part of the circle will be another 5 volts. And I'll show you in the simulation an example of that. Okay? But that basically means that the voltage will be the same. Now I want to point out a thing about terminology. Another word for voltage is potential. Sometimes people use electric potential. So if you ever see a word called electric potential or potential, they're really referring to voltage. So another word for voltage is potential. Now, another point that I need to make out is that the local direction of a given electric field is tangential to the field line. So what does that mean? What are we meaning by local electric field? Well, let's say that we put our test point here, and we want to know what the direction of the local electric field, like your local supermarket, it's in that location. Well, the local electric field is always going to point pretty much in the direction of these arrows, right? So tangential would be like this. So if you don't remember what tangential means, you might have saw it in Physics 1, maybe you had something rotating, and they're like, calculate the tangential velocity, right? So here's a point, a tangential line would be right on that, the straight line along that point, like the path it would take if you take the slope at the point. It's kind of a calculus idea, but that's what tangential means. So when you look at your graphs, and they say, oh, what is the tangential or local electric field? It's going to be like at this point where my laser's at, it's going to go straight along that arrow, okay? And if it's right here, it's going to be going this direction. That's the local electric field, which is important, right? Because if you have devices and you want to know what the local electric field is and you have these charges in the area, that's something worth knowing. So that's what local means. And then, which brings me to one of my final points is, the electric field is going to be stronger where there's more lines per area. So an example of that, right? You can look right here. There's not that many lines, right? So the electric field out here is kind of weak compared to the electric field right here. All these lines are wanting to converge in one area. So the electric field will be stronger here versus out in the middle of nowhere. So that's another thing that is worth pointing out, that the electric field will be stronger when you have more lines per area. So that's how we're going to read these diagrams, and that's what we're going to be doing this week in this lab. We're going to be measuring the electric field along a straight line, and then we're going to be looking at some of these diagrams. So let me go to our lab so I can show you what we're going to do. So just like last week, we just covered the introduction, but you're going to have a procedure. You're expected to go to the link, and I'm going to talk about some of the things in the simulation just to clarify for you this week. But essentially, you're going to have two parts. Part one of your lab, you're going to be looking at 2-point charges, all right? And I'll give an example of that. You're expected to follow the procedure. Now, when I'm giving an example, I might not be following the procedure exactly, but when you do it, you're expected to follow the procedure, use the appropriate distances that they tell you, because your results will be a little different if you don't. The second part is they're going to want you to look at 2 line charges or 2 parallel plates, and I'll show you how to do that correctly. Students usually make little errors each year, so I'm going to try to make it a little clear for you. And then, just like last week, you're going to have your worksheet. Now, number 1 and number 2, I have a video where I give an example on what it means. So I'll post another video that will clarify what these questions are asking. Again, 3 and 4 are exactly like 1 and 2, so I'll show you guys in a video how to do 1 and 2, so it should be really easy to do 3 and 4. And of course, you're going to have similar questions about the lab like you had last week. So I'm not going to go over any of that, but what I will do is I want to clarify what they're going to be asking you for a lab. So let's show you what you're going to be doing for your first lab. So for your first lab, they're going to ask you to look at 2-point charges, right? Again, I want to point out that all the arrows are pointing away from the positive charge, and you're going to see when I put this negative charge that all the arrows are going to be pointing towards negative charge. So this is basically what your first procedure is going to ask you to do. They're going to tell you to put these at some distances apart, and you can turn on the values and stuff where it shows you the distances, like 2 boxes is 1 meter, and you're going to have a little measuring tape that you can measure the distances. So set these up at the appropriate distance. You're also going to be expected to take things like the voltage or use these sensors, right? Where they tell you the electric field at the sensor. So use the tools and follow the instructions. Again, they don't draw the equal potential lines here in the simulation, but just to show you, like you can imagine that if we have a circle here, like I showed you in the diagram, that the potential will be the same, right? It's 15 volts here. We follow that circle. You'll notice how it should stay around 15 volts. So if you draw a perfect circle, you'll notice that along those lines, your potential will be the same, right? So you can kind of see, just playing around with it, that it should stay around 15 volts if we try to draw a good circle. Now the second part of your lab, they're going to ask you to do 2 line charges, and this is where students make a mistake. Sometimes they put the charges too far apart, but what you're going to do is you're going to have 13 charges, and you're going to try to put these not super close together, but not super far apart. So you kind of want to put them where they're barely touching, and you're going to make 13 charges. Now this is an example, so I'm not going to do all 13 charges, but you're going to do the same for your negative sides. Turn the grid on, that way you can follow the line, so it's easier to do. But you get the idea. So you'll have 13 charges up and down like this, and what you're going to notice is as you have these 2 parallel lines, or parallel plates, that the lines here are going to be more straight, more uniform, and versus less fringe. So your electric field will be more uniform between these two. That makes sense because a positive charge is going to want to flow towards a negative charge. So you'll have some fringing on the other side where these lines curve a little bit and come back down. But you'll notice that your electric field should become more uniform in this area when you have the parallel plates. And they're going to be asking you questions about that in your lab. So if you have any questions or if you have any trouble, please feel free to come to office hours on Wednesday next week, or send me an email of whatever questions you may have, and I'll post another video that will clarify number 1 and number 2 a little bit more. Well, thank you for listening, and have a good week.